We have started the discussion on bending of beams or beam statics in the previous video in this playlist. We just continue with the same topic here, and in this video we try to analyze the equilibrium conditions of the beam statics and try to mention the creation of shear force and bending moment diagrams. So we continue analyzing the beam statics. So we have discussed the different types of loads as a point load, a uniformly distributed load, and a uniformly varying load in the previous video. So you have three types of loads, and you have also discussed the different types of supports. You have a roller support, a pin support, and a fixed support. A roller, pin or hinge support, and a fixed support. We discussed a roller support can only provide resistance in normal direction. A pin support can provide resistance on two planes or on same plane in two axes, so x and y axis, and a fixed support can provide resistance in two axes, and it can also resist a moment. So let's see how we can analyze a beam bending. Now that we have discussed in previous videos that the equilibrium conditions of a beam or stress, or for generally for force equilibrium, you need to satisfy three equations. So for force equilibrium, you need to satisfy three equations. Basically, they are summation of forces in x direction is equal to 0, summation of forces in y direction equal to 0, and summation of moments in z direction equal to 0. So these are the three equations again when you do the analysis of beam bending, or you calculate the shear and bending moment diagrams. Now let's see how we can do the how we can apply these equations in beam statics. Let's start with a simple beam here, as shown here. Let's assume you have a simple beam like this, and you have a roller support in here, and you have a pin joint here, and suppose the beam is of say 4-meter length, and there is a load at the center of the beam of for say 10 kilonewton, and say the distance to the that load is 2 meter. Now how we can analyze this beam here? Let me move that beam slightly towards the left side so that I can let me place it here. Now how we can analyze this beam? First of all, you need to calculate the support reactions, and for that this is a symmetry case where you have 10 kilonewton here, and which is acting at the center of the beam. Now as I said before, you have three equations: summation of forces in x direction equal to 0, forces in y direction equal to 0, and summation of moments in z equal to 0. Now as you can see, there is only vertical loads, so this condition is satisfied already. And for y direction equal to 0, you should have, say if this is A and this is B, then you will have RA here, which is acting upward, and RB here, which is acting upward again. So RA plus RB equal to 10, which is this condition, or Ri plus Rb minus 10 equal to 0. And now you also need moment. about the z axis equal to 0. So let's take a moment about A. And that will give you 10 kilonewton acting at a distance 2 meter from A. So 10 into 2, that is a clockwise direction. So 10 into 2, and RB acting at 4 meter. So, and that will create, based on A, RB will create a counterclockwise moment like this in this direction. So minus RB into 4 equal to 0, or RB equal to 20 by 4, which is equal to 5. And if you substitute that 5 here, you have RA plus 5 equal to 10, and therefore RA equal to 10 minus 5, that is equal to 5. And you don't have to do all these because it's a case of symmetry. It is acting at the center, so you can say RA and RB equal to 5 each. Now I'm going to extend this beam to here, and let's call this as the center line. Let me use a straight line here. So this at RA and RB you have 5 kilonewton each, and at 2 meter you have a 10 kilonewton force on this beam. Now you can see RA and RB are acting upward, and this 10 kilonewton is acting downward. So in order to create the shear force diagram for this force condition, you have your A here, you have your B here, and you have your middle point, let's call it O here. So at A you have a force acting 5 kilonewton acting upward, that is your RA, and this is 5, and that force is constant until it reaches this point here at the midpoint. And at the midpoint, as you can see in the original diagram, you have 10 kilonewton acting downward. So just write that or draw that 10 kilonewton acting downward at point O. So the magnitude of this is 10, and that force keep the same until it reaches the point B, and from where you have a 5 kilonewton acting upward. So this is 5, which is RB, and thus you have the closed shear force diagram. So this is your shear force diagram for that case, and you don't really have to draw these 5 kilonewton all on here. You can simply show that. I'm just explaining. I'm just drawing it again to show you a bit more clarity. So you have your original force here. Sorry, the reaction at A here, and you have your the same force reaction at A going until the middle of the beam here, and then you have the same magnitude coming downwards, which is 10 kilonewton, that is the acted load, and then you have same force acting until point B, and then you will have reaction at B acting upward. So you have a 5 kilonewton here, and this is total 10, but here it's minus 5 because it's below the datum line, and then you have another 5 kilonewton here, so it will be 0 again. So minus 5 cancels here with the RB here, RB, and this is RA, and this is the applied force. So that is your shear force diagram for a force condition like this. Now, in the next video, we will see how we can create the bending moment diagram for the same force case. Thank you.